Welcome to Zero Rocks Unstuck. Today, binary search. How to find something in a sorted list in a handful of steps instead of scanning the whole thing. It's simple in theory and famously easy to get wrong, so we'll build a bug-free version from scratch in Rust. Well, say you have 10 million sorted numbers and you want one of them. Jatash checking from the start can take 10 million comparisons, but the binary search does it in about 24. Let's see that difference for real. If you're prepping for interviews, a quick like helps a lot. Let's start with the slow way, so the fast way. Clicks, linear search. Walk from the front, check every element, stop when you find it. We also count the comparisons so we can compare fairly. It's ON. The work grows with the size of the list. Search 10 million numbers for one near the end. Found it, but it took 10 million comparisons. That's the cost of ignoring the fact that the data is sorted. Linear search throws away a huge advantage. The list is sorted, but checking one element at a time doesn't use that at all. We can do far better. Please don't think about finding a word in the dictionary. You don't start at page 1, you just open the middle, see if your word is before or after, and throw away half the book. Then you repeat on the half that's left. And that halving is binary search. As the catch, it only works if the data is sorted. In code, we keep two markers, low and high, for the range we're still searching. Look at the middle. If it's the target, done. If the middle is too small, the answer is in the right half, so move low past mid. If it's too big, the answer is in the left half, so bring high down. Here it is in Rust. Low starts at 0. High at the length. Note high is exclusive, just past the end. We loop while low is less than high, meaning the range still has elements. The middle. Mid equals low plus high minus low over 2. You might expect low plus high over 2, but on huge indices that sum can overflow. Low plus the half distance gives the same midpoint and never overflows. This is the line people get wrong. Then the three cases. Equal, we found it. Middle less than target. The answer is to the right, so low becomes a mid plus 1. Otherwise high becomes mid, because high is exclusive, mid plus 1, and mid keep the range shrinking and never loop forever. Run it, same 10 million numbers, same target, now found in 23 comparisons. 23 versus 10 million. 10 million comparisons down to 23. That's because each step halves the range and you can only have 10 million about 24 times. That's what log n means in practice. Trace a small one. Find 7 and 1, 3, 5, 7, 9. Middle is 5 too small, go right. New middle is 9 too big, go left. New middle is 7, found in 3 steps. Binary search is famous for bugs. The big three, computing mid as low plus high over 2, which overflows, mixing up the loop bound and the exclusive high, which reads past the end, and not actually shrinking the range, which loops forever. Our template, with high exclusive and low less than high, avoids all three. One hard rule. Binary search only works on sorted data. If your data isn't sorted, now you either sort it first, which is n log n, or you use something else like a hash set for O1 lookups. Complexity O log n time. The beautiful part, double the size of the list and binary search needs just one more step, and it uses no extra memory. The Rust details: use size for indices, the overflow safe midpoint, and the half open range with high equal to length and the loop condition low less than high. Memorize this template and you'll never write a buggy binary search again. Recap: on sorted data, look at the middle and throw away half each step. Use the overflow safe midpoint, move low or high to shrink the range, and you've got binary search in O log n. Quick one, if these help you, the wallet's on screen and there's a Ko-Fi link in the description. Every tip funds the next one. The full Rust code is in the description. If this helped, hit like and subscribe. A new coding challenge every day. See you in the next one.